Hello, my name is Zachary Chenoweth, and this is my presentation of Lab 3, Task 2, Measurement Estimation. Now for this lab, we have to use triangulation or trilateration to calculate the robot's position as it moves through this grid cell, and it has to visit all the cells in this grid. So starting off with the code, we're going to go ahead and look. Here we have all the normal initializations for the robot. This includes the camera, the distance sensors, the IMUs, etc. Here we have the initial positions and colors of the cylinders, which we will use later for the camera recognition. Here I have just a simple array to hold the visited cells. The star designates that we have not visited that cell yet, and the X designates that we have. Since we always start in cell 16 facing north, we're going to go ahead and put an X starting out in that grid cell. Here we have just some variables that we use to initialize the orientation, the angle, and the cell. Just because, again, like I said, we will always be starting in cell 16 facing north, which is about an angle of 180 degrees. The first function we have here is my calculate velocity function. This is for calculating the velocity for the turns. For this task, I decided to not use the IMU value for either the noise and non-noise solutions, just because I found it a little bit more simplistic to do it this way. So it uses the kinematics formulas to calculate the velocity, so that way we can turn the robot. The next thing is our forward function. We use the left position sensors. We first get the starting position before it moves, and then we are going to have the robot move about 10 inches forward. So it's going to constantly read the distance traveled, and as soon as the distance traveled becomes greater than or equal to 10, it's going to stop the robot. Otherwise, it's going to keep moving forward at a speed of 3.14 radians per second. Now, the reason I chose this speed is just because I didn't want the robot going too fast, and the speed we set the robot to was at our discretion, so I just found it easier to do it this way, just to prevent any hiccups or anything along the line, just in case. Here we have our turn function. This just turns the robot 90 degrees in 1 second. So we call that calculate velocity function we did earlier to turn 90 degrees in 1 second. And then it's gonna turn while the time passed is less than a second. So that way we turn the full 90 degrees. And then as soon as that's done, we're gonna go ahead and stop the robot and update the orientation. And then return the orientation. Here we have our change angle function. This basically will just update the angle to our new orientation. So if it's north, the angle is 180, south is 0, east is 90, and west is -90. And then we return the angle. Here is the actual function for trilateration. This function, we start out by getting the radiuses of 3 cylinders of our choosing. So for all the cells that are not these designated cells with the if statements, are going to be using the radius of the yellow cylinder, the green cylinder, and the blue cylinder. So we give it the radiuses and the positions, those X and Y coordinates that I showed above of each of the cylinders. These radiuses are calculated in a function that's later down the list, so we will go to that in just a second. As I was going through this lab, I did find that sometimes in certain cells, especially the corner cells, so cells 4, 1, 13, and 16, sometimes specific cylinders gave me a more accurate result if I use those radiuses than others. So after some trial and error, I found that for cell 4, I wanted to use the green, blue, and red cylinders when it's in cell 4, so this cell right here. I found that to help it be more accurate. Cell 1, I wanted to use blue, red, and yellow. And then cell 13, I wanted to use red, yellow, green. Here's all the formulas for the trilateration that we were provided in our lecture notes. We use these formulas to calculate our x and y coordinates. I put that in a list to called current position, and then I return that current position. This function called reject outliers is just to prevent any outliers from when we take the averages when we're calculating the radiuses. All it does is basically say if the value, the distance that we read in our list of distances from this cylinder, which I'll explain further later down, if that value that we're reading is within plus or minus 2 standard deviations away from the mean, then we're going to keep it. Otherwise, we're just going to discard it from our list. So this is to remove any outliers from our averages. This function cylinder radius is what we're going to use to actually calculate the radiuses of the circles around the pillars by using the distances to each pillar. So we have a few lists to keep a hold of these values. This distance list holds the distances in to the yellow cylinder, the green cylinder, the blue cylinder, and the red cylinder in that order. And then this radius thing will, this radius array will hold our final radiuses of each of the pillars in that same order that this distance array is when we append them to this list. So in order to get the distances, we have to make the robot turn. And instead of using the IMU, I decided to turn based on time. So I calculated using kinematics the amount of time needed to turn 360 degrees in, like, I needed the time take to turn 360 degrees at a given speed. In this case, our given speed is 1 radians per second. So it takes about 8.96 seconds to turn 1 radian per second to turn 360 degrees. Again, I just use the simple kinematics formulas to calculate this number. And then as the time is less than this number, we're going to go ahead and look for the object. So if the number of objects that we recognize is 1, because as it's turning at multiple points when the distance sensor, the front distance sensor is actually facing centered on the cylinder, only one object will show up in the camera. So if the number of objects is just 1, we're going to go ahead and create a camera recognition object. If that camera recognition object is yellow, green, blue, or red, it's going to go into the respective if statements. And then we're going to say, while the distance sensor is centered on the cylinder, so we take the x coordinate of the get position of the object, which is how we know how centered we are. The closer we are to 0, the more centered it is. So we go ahead and use the value of 0.03 just to give us some room so we can get more values for the averages. We're going to take that distance that the front distance sensor is reading and append it to that array that I had earlier to the respective list for color in the order that I mentioned before. And it's going to do that for each of these colors, and it's going to do that until it's turned all 360 degrees. Then it's going to stop our robot, and then we're going to remove any outliers and calculate the mean to get our radius for each of the cylinders. And then we're going to return the radius. Print info here is just going to go ahead and print the information, the X and Y coordinate, the current cell, and the angle. And then our next function, update grid, is going to update that grid that I showed you earlier. It's just going to go through, and if we're whatever cell that we're currently in, it's going to mark it with an X, and then it's going to print the grid and return the cell that we were in. Check visited will basically check if the next cell that the robot is attempting to go to has already been visited. So that way we prioritize non-visited cells first. We do this by adding and subtracting 4 and 1 respectively, depending on which direction we're facing. So if we're going north on the grid, then we're going to go ahead and subtract 4. South, we're going to add 4. East, we're going to add 1, and west, we're going to subtract 1. And that'll give us the index for each of these grid cells. And then it's going to return 1 or 0 to say whether or not we have visited that cell or not. The check done function is just going to check and see if we have visited all the cells, so that way the robot knows to stop and the program will end. And then we have our main loop where we're going to do all our calculations, print the information, and then do our motions. So now that we've ran through the code, let's go ahead and see it run. So as you can see, it's going to start off by turning, getting the distances from each of these cells, so that way it can perform trilateration. And then once it's done, it's going to go ahead and give us the current position that the robot has. And you can see that it also updates the grid cells as it's moving. So because we're using the trilateration formulas to calculate the actual coordinates, it's going to be off slightly from the actual coordinates that we're at. But each of these values are going to be within plus or minus 3 inches from the actual value. And you can see it's just going to keep updating the grids and as it goes. Some of the X and Y coordinates that we calculate are going to be very close or exact, and then some other ones will be slightly off. This could be due to just some slight error in the averages or in the readings. So as you can see, at each cell, it's going to stop and do this turning motion to get the distances from each of the cylinders, so that way it can perform the calculations, and then it's going to continue forward. One of the reasons why I decided to make the turning motion only go 1 radians per second is because I wanted the robot to have enough time to take values as it's passing the cylinder to get enough values to make a better average. Because if the robot went too fast, then it won't get as many values, if any at all, if it goes fast enough. But I didn't want to go too slow as well, as we don't want the program to run for 15 minutes or so. As you can see, we're getting close, and the robot recognized that it had already been to this cell, so it decided to turn to prioritize this cell over this one. And so it's going to move here and perform trilateration again. And it's going to finish off going through these last few cells here. Again, when the robot finishes here, it's going to see that it's already visited this cell, so it decides to turn rather than move forward. And then it's going to get this last position from the cells. And that ends the program. So now all the cells are visited. We have all of the robot poses as it went through the grid, and it ended the program. So that's the version without noise. Now let's go ahead and take a look at the version with noise. So this one is fairly similar to the previous one with a few changes. So again, we have all of our initializations, our positions and colors for the cylinders, the grid cells, our initialization variables. Calculate velocity is the same. Forward position, this forward function is the same. Now the reason it's the same and it's not any different, despite there being noise now to the position sensor, is because the way this code's set up, for some reason for me, didn't affect the actual outcome. So despite there being like 25% noise to the position sensor, because the way the code is set up, the values will always come out about the same. So the distance traveled will be about 10 no matter what. So I decided not to change it. So I left it the same. The turn function is exactly the same. Change angle is the same. Trilateration, we have some differences. You can see that I have edited a few of the radiuses, so the pillars that we want to pick per cell, and I've updated these. I found that these were easiest to use. Now, cell 16 is going to be a unique case. Since we know that we start in this cell, I decided later down the line for the X and Y coordinate that we don't really need to use trilateration since we know that's where it's at and where it starts. So I just made the robot, I hard coded the position to be in that starting position, but every other cell will use trilateration to calculate its X and Y coordinates. Cell 16 is the only one that does not do that because we already know its starting position. So we choose the cylinders and we get the positions of the cylinders. We perform our trilateration formulas to get our X and Y coordinates, and then we return the current position. Our reject outliers function performs the same as it did in the non-noise solution. We basically check to see if each value is within 2 standard deviations of the mean. And if it's not, then we filter it out as an outlier, so we don't want it. Our radius, cylinder radius, is very similar to the previous one. One of the major differences from this one is that I increased the range that the robot will get values from, because now that there's noise to the sensors, we want to be as accurate as we can be with the values. So the more values we can get, the more accurate we can get an average for the radius. So I decided to extend it, but I didn't want it to extend it too much because then the radius becomes too messed up and it's not as accurate. But other than that, everything here is the same. And then we return the radius. print information, update grid cell, cells visited, and cell check done. Those are all exactly the same as they were before. And then in our main loop here, we have our functions and stuff as they were before. And this is where I was talking about how cell 16, since we already know its starting position, I just hard coded that position there. Every other time we're going to go ahead and perform trilateration. Again, that's just because we know the starting position of the robot as this. So I didn't see any need to perform trilateration since we already know its position. All right, so now that we've gotten that out of the way, let's go ahead and see the robot run. So one weird glitch that I found is, despite us not needing to perform trilateration, if it didn't have the robot do this turning motion, all the trilateration calculations later down the grid cell would be completely out of range for some reason. So I saw that it didn't have any mess ups as long as I had it turned first, so that's why it turned anyway, despite us not using trilateration to calculate these values. So as you can see, the calculations are again a bit off. They're not as exact as the non-noise solution, and that's because there is noise to the sensors. I tried to take care of it as best I could using averages and getting rid of outliers. But sometimes we get lucky and we get exact values as we want. But all these values that are calculated are within plus or minus 3 inches, which is the given range that we can have as error, as per the description of the lab task. So as you can see, it's moving through, it's updating the XY coordinates, the grid number, the cell number, and the angle, as well as the grid itself, so we can see which cells we visited. And it's going to keep going through, so I'm just going to go ahead and speed this up, since it's basically going to, at this point, is doing exactly what the last one did. So let's go ahead and speed it up. You can see it's spinning, it's going through, and we're getting all our values. And then once it's done, it's going to go ahead and end the program. And if we look up, we can see all the values that it calculated as it goes through. And you can see that they are within plus or minus 3 inches of the actual location. So that was Lab 3, Task 2, Measurement Estimation. Once again, my name is Zachary Chenoweth, and I hope you have a wonderful day.